We have already discussed different curvilinear coordinates, and among the curvilinear coordinate systems, the most important ones for this course are spherical and cylindrical coordinate system, because we will encounter systems with spherical and cylindrical symmetry. So, if we consider spherical coordinate system, we have already discussed earlier that x can be written as r sin theta cos phi, where r theta and phi are defined over this kind of a sphere. This is the x axis, this is the y axis, and this is the z axis. If we have a point P here, then the angle that position vector of point P makes with z axis is called theta. The position vector itself is called r. So, the distance from the origin to that point P is r, and if we project this onto the xy plane, we will find that the projection makes an angle with the x axis. That angle is phi. So, we can write down that x equals, x is this much length, y is this much length, y is this much length, x equals r sin theta cos phi, y can be given as r sin theta sin phi, and z is given as r cos theta, that you can clearly see from here. And a vector A in spherical coordinate system is represented as a r cap plus a theta cap plus a phi cap, where a r is the radial component, a theta is the theta component, and a phi is the azimuthal component. With this, we have already found out its relation with Cartesian unit vectors. Now, let us consider the line element, surface element, and volume element for spherical coordinate system. A line element along R, let us write it down as dl with subscript r, that is nothing but dr. If we consider the theta component of the line element, that would be r d theta, which is clear from this picture. If you move r in this direction to increase the value of theta, so the distance it will travel is r d theta, r times the change in theta. Similarly, dl, the phi component of the line element, can be given as r sin theta d phi. So, we are projecting this onto xy plane and then changing the value of phi. That means, we have the radius of that projection as r sin theta, and the change in angle is d phi. So, along phi direction, the change in the length is r sin theta d phi. So, the line element vector can be written as dr r cap, plus r d theta theta cap plus r sin theta d phi phi cap. With this, we can easily find out the volume element. The volume element d tau can be given as a triple product of this, or simply multiplying dl r component with dl theta component and dl phi component, which is given as r square sin theta dr d theta d phi. Now let us come to the consideration of surface elements. In case of spherical coordinate system, we can certainly have different surfaces in here, and if we consider the surface of the sphere, the curved surface of the sphere, then this is the origin, here is the z axis from which we will measure theta. Then we can see that if this much is r, then r d theta will give us the distance along this direction, and we will have to multiply it with a perpendicular component. So, we will have to consider the phi component, that is r sin theta d phi, that will give us a component along the phi direction. So, for a surface element on the surface of the sphere, we will have to consider r as constant. That's the time when we will travel along the surface of the sphere. So, one component would be r d theta, and we will have to multiply it with the other component r sin theta d phi. Now, because surface element is a vector, we will have to consider theta cap direction here and phi cap direction here, and it will be a cross product. Let's tell that this is the first kind of surface element vector. That means it is given as r square sin theta d theta d phi, and the cross product of theta cap and phi cap will give us r cap. This would be the first kind of surface element. Now, if we consider the xy plane, if we are trying to find out a surface element on the xy plane, then what are the variables? We can have r varying, we have theta fixed, and phi can also be varying. So, on xy plane, we will have theta equals constant equals pi by 2. With this, we will have dA2, the second kind of surface element, as dl r cap cross dl phi phi cap, which is r dr d phi theta cap. Please note once again here that the range of R is 0 to infinity, the range of theta is 0 to pi, and the range of phi is 0 to 2 pi for spherical coordinate system. Now let us consider an example. We want to find the volume of a sphere of radius capital R using the volume element that we have just found out. So, the radius of this sphere is capital R, and we will perform a volume integral on the volume element that we have found out. So, the volume V would be given as integration over d tau, and here we will have to find the appropriate ranges for r theta and phi. We will have to perform 3 integrals, 1 over r, 1 over theta and 1 over phi, and the integral will be performed over only d tau, the volume element, that is r square sine theta dr d theta d phi. So, the range of R would be R equals 0 to capital R, the range of theta would be theta equals 0 to pi, and the range of phi would be phi equals 0 to 2 pi. Now, we need to perform the integrals, and this integral would become integration over 0 to capital R r square dr times integration 0 to pi sine theta d theta times integration over 0 to 2 pi d phi. We can separate these integrals because none of the functions depend on each other. For example, the function of r depends only on r, not on theta or phi, and similarly for theta and phi also there is no dependence on each other. Therefore, we can separate it this way, and with that from r part we get r cubed over 3, from theta part we get 2, and from phi part we get 2 pi. That gives us 4 over 3 pi capital R cubed, and this is the well known expression for volume that we all know. Now, let us consider gradient in spherical coordinate system. We will not derive the expression. We have already discussed how we can derive it. So, we will just write down the expression for your reference. Gradient of a scalar field T is given in spherical coordinate as del T del r cap plus 1 over r del T del theta cap plus 1 over r sine theta del T del phi cap. We will give you the expression for divergence as well in spherical coordinate system. divergence of a vector field V is given in this coordinate system as 1 over r squared del r of r squared times the r component of the vector Vr plus 1 over r sine theta del theta sine theta times the theta component of the vector V theta plus 1 over r sine theta del V phi del phi. This is the expression for divergence, and finally the expression for curl in spherical coordinate system can be given as curl of a vector field is expressed in spherical coordinate system as 1 over r sine theta del theta sine theta V phi minus del V theta del phi r cap plus 1 over r 1 over sine theta del Vr del phi minus del r r V phi theta cap plus 1 over r del r r V theta minus del Vr del theta phi cap. This is the expression for curl, and after this we will have to give the expression for Laplacian, that is del square in spherical coordinate system. Let us consider a scalar field T on which this del square is applying. So, we can write it as 1 over r squared del r squared del T del r plus 1 over r squared sine theta del theta sine theta del T del phi del theta plus 1 over r squared sine squared theta del 2t del phi 2. This is the expression for the Laplacian operator del square in spherical coordinate system.